So back in 2004, I was in grad school and I took an entire course on design of experiments. It was one of the most fantastic and practical courses I took in grad school. And at the time, I understood the theory, like the statistics, the orthogonal arrays, the interaction plots, but I didn't fully yet appreciate how much I would rely on it throughout my career as an engineer in industry. And that appreciation came very quickly once I started using it. When I worked in the pharmaceutical industry and both the semiconductor industry, DOE became one of the tools that I reached for constantly, and it was one of the most heavily used statistical tools that I used during those years in industry. So one of the times that really proved valuable was when I was starting to work on the softgel encapsulation machine, and I was tasked with creating a mathematical model of how that machine worked to help automate it. So we wanted to test also in research and development, new gel formulations, optimize the machine parameters, like such as temperature, machine speed, and airflow. So this is the type of problem where you have several variables and you need to understand how they interact because changing one at a time can sometimes yield very similar results to when you change the other variables one at a time. So I mean the results can be confusing. So you need to use statistical techniques to clarify what's actually happening and what the relationships are between parameters. So we started the way that most engineers start. At first, we changed one variable at a time. We tested temperature first, tested airflow, then speed, and then it quickly became obvious that this approach was going to take forever. And not only that, changing different combinations of the machine parameters yielded very similar results. So we were having a difficult time picking apart each variable contribution and the intensity of the interaction between variables. So sometimes when you're just looking at one variable at a time, you can't really tell how they're interacting with each other. So, and the more complex the manufacturing processes become, sometimes those interactions become more important than the actual main effects. So I thought back to my course I took in grad school in 2004, and this is the exact problem that DOE was designed for. So that realization changed how I approached every experimental problem for the rest of my career. So not only in manufacturing, but in research and development as well. So in this video, I'm going to explain design of experiments from the ground up and implement two of the most important designs in Python from scratch. We'll start with the full factorial design, which is definitely not the most economical, but we'll go into fractional factorial and then Taguchi orthogonal array methods, which I used the most actually in the past. I used this extensively both in pharmaceuticals and semiconductor manufacturing. So my name is Colleen Spiegel, and this is Python for Scientists and Engineers. So what is the design of experiments and why does it matter? Design of experiments is also known as DOE. It's a systematic approach to planning experiments so that way you can extract the maximum amount of information from the minimum number of runs or tests. So let me explain why one factor at a time is not just slow, but it's fundamentally flawed. When we were working with that softgel encapsulation machine, we were interested in actually 5 main factors. Some of those included temperature, airflow, and machine speed. And if we change the temperature while holding airflow and speed constant, we learn how the temperature affects the outputs at those specific settings. But we have no idea whether the temperature behaves the same way at a different airflow setting. So that relationship between variables, how the effect of one variable affects another one, is called interaction. And the one factor at a time experimentation approach cannot detect interactions whatsoever. So this matters enormously when working with multiple variables. So I've seen manufacturing processes where the optimal temperatures at low machine speeds were completely different from the optimal temperatures at high machine speeds. So an engineer that only changes one variable at a time would never find the true optimum between all of these variables. So they would optimize each one locally and miss the actual global relationship between the variables. So DOE actually solves this issue by choosing which combinations of variable settings to test so that all the main effects and the most important interactions can be estimated from a reasonable number of experiments, not, not tens or hundreds or thousands even. So the key terminology that I want to introduce are factors and interactions. So factors are the variables you control. Those are called the inputs. So in this particular example that I'm speaking of in pharmaceuticals with the encapsulation machine, that was temperature, airflow, machine speed, gel type, and there were many other parameters as well. So the factors are what you're manipulating. And the levels of those factors are the values that each factor takes. So in a very simple case, a two-level design, each factor has a low value and a high value. And so the reason is you want to cover the range that each variable is operating at. So then you have the response or the output. So this is what you want to optimize. And so in our case, in this example, it was capsule weight, yield, dissolution rate, shape quality. There was many other outputs as well. So this is different for each process. So a run is a specific combination of factor settings, one experiment. And an interaction is when the effect of one factor depends on the level of another. So the one factor at a time thing can never find the true relationships between the variables, the inputs and the outputs. So this is what DOE is specifically designed to reveal. So let me share a few more examples from my pharmaceutical and semiconductor years, because I think they illustrate how broadly the DOE applies and how critical it becomes when the stakes are high. In semiconductor manufacturing, I use DOE extensively for electroplating processes. So some of those inputs or variables were plating chemistry, plating speed, temperature, bath composition. All of these variables interact in a way that affects the outputs, which in this case were copper thickness, uniformity, and adhesion. So a plating process that looks acceptable at one combination of settings can produce completely different results when you change the chemistry slightly or increase the plating speed or increase several of those variables at once. So DOE gave me the ability to map those interactions systematically rather than discovering them the hard way during production. I also use DOE for photolithography coating processes, studying how the spin speed, coating temperature, humidity, and material viscosity affected coating thickness and uniformity across a wafer. So in photolithography, every micron, or in some cases nanometers of thickness variation matter. So when you change one factor at a time, it's not just inefficient in this environment. It's actually could be dangerous because you could optimize one parameter and unknowingly make another parameter worse.